Hello, this is Dr. Heidelberg, and our presentation today is programming in mechatronics. We'll follow the textbook of Bolton, 4th edition, and the topics will cover C language. We'll take a look why we're using C, program structure, examples, and also see an example of motor start-stop. We also take a look at the peripheral system interface, some devices, interfacing, interrupts, programming, transmission, display, and analog digital converter. Why do we use C? It is often used in programming microprocessors. It is easier than assembly language. It's standardized by ANSI. And all we need is a compiler to translate it to machine language. The structure of the C language, it starts with a preprocessor. It then has the main program, and the main program includes functions, which are the subroutines, statements, and they are included with curved brackets. We see here an example of a Hello World program. It starts with a preprocessor and include the library functions. We have, in this case, the standard I/O. We can also have math or time. We include them in a preprocessor. And then we see that we have here the main program. When we have the two forward slashes, this is a comment which is not being considered by the program. And then we have here a program, a print function of Hello World. It is enclosed in parentheses and also in quote, starting quote and closing quote. And then the main program is ending with a return of 0, and 0 stands for the definition of the type that the program returns. And this particular case, it is an integer. We can also have floating, double, and characters when we define variables, and we'll see in the next page. The brackets could be either the curly to enclose the program, the statements. They can have the round brackets that enclose the function parameters, such as we see over here, main. And then we have the angled brackets that enclose the library functions, and then the square brackets that enclose arrays. We could take a look here at the general process of doing programming for a mechatronic device. We start by creating the code in an editor on a PC. Then it is going to the compiler to generate the source code, and then the compiler will provide us with error messages, and we'll go through the process of debugging. When we eliminate the bugs, the compiler will proceed to generate the machine code. And then it will be linked with the preprocessor header library, could be also microprocessor registers and ports. And this will then generate the executable file. Executable file is downloaded to the chip, and then it can be used on a PC board to drive a device. The learning of C programming could be done with various online sources. Here is one of them. If you click on that icon, you could reach that, and this will go you through all the program pneumatics and examples of the C language. Here's an example of an online compiler that we could get for various programs. There's almost 20 of them here listed. The first one is C, and here's an example of what it looks like. You get it online and you run it in a cloud, so you don't have to download the C program on your personal computer. In this example, you see that once you run the program, it's the same program as Hello World that we saw earlier. Then we get the result over here on the screen. It says over here, Hello World. Here's another example of using the editor to write various small program of multiplication. We have the header with a library of standard I/O. We define integers A, B, and C, and we define also a integer main in the curly brackets. And in the main, what we do is we define a variable A equal to 5, variable B equal to 6. Each statement has to be ended with a semicolon. And then we define C as A times B, and then print function of C. And then we have the percent sign D within the quotes, and then comma C. What that means is that when we print the value, what we like to do is print C equals, and then print the value of C, and D is a signed decimal. If we have C over here instead of D, it'll be a character, or if we have F, it'll be signed floating. And as a result, we see over here, then we run the program, we get C equals 30. Here's another example, writing a program to calculate the cylinder volume with user input parameters. So we have the same headers as before, but we also add the header of math.h. And then we define a constant floating point variable called pi, and we set that to 3.141. And then we also define location, memory location for parameters rad, height, and volume. And then we have a function over here. Float is the type of the result, which will return from the function. And then the name of the function is cylinder volume. Usually you use the variable, two words could be combined, cannot separate them. And then we define to make it clear by lowercase and then the capital letter for the second word. And then we define within the function the parameters. This is R and H. This is the radius of the cylinder. This is the height. Both of them are floating points, so we define them right here. And then we say float is another variable, V. And we define the function V equal pi times R squared. This is the base. And in order to raise R to the second power, we use this command, power, this function, power, which is part of math, with the parentheses, R comma 2. This will square R, and then we multiply this times H, and the return will be V. So that is a function in a header, and it will be called from the main program. So the main program starts with the bracket, and then we put the scan function. And what we'll be scanning is the floating point, F, okay? This is the percent sign with F, meaning that we will be defining the parameters that we'll put on a terminal as rad, and then the second one will be floating height, and then we'll define volume as cylinder volume. We call in this function, and the parameters that we transfer to the function is rad for R, and height from H. And these parameters will be determined by the terminal when we input them. And then when we're done, we print the rod as a floating point, and then /n will take a new line, and then this will be bringing rod over here after the equal sign. And similarly, we do for height and volume, and then we turn 0 on the main, and the result here is 2.5. This is what we entered on the terminal. 4 is for the height, and then the printer gives us 2.5 in floating point for the rod, 4 for the height, and then the volume is calculated 78.525002. So this is another example how we may start and stop a motor on a Motorola 68H C11 microcontroller. So we have over here a switch that when it is closed, we like to start the motor, and another switch that when we close, we like to stop the motor. So these two switches are connected to the PC 0, and over here to 1, and the output is going to be in PB 0, and that goes right to the driver of the motor. So the port, this is pin 0 of port C, and this is pin 1 of port C, and this is pin 0 of port B. These will be the 2 pins on the input and 1 pin on the output that we'll be using. So we have a header over here, which includes the Motorola microprocessor library. It's defined as HC11E9.H. And then we start the void. And the first statement says that we initially ensure that the motor is off. And the statement says that we take the pin 0 on port B, and we end it with 0. So when only way that we can have 1 is if both of them are 1. So if we add it to 0, it must be 0, and that will turn the motor off. That switch is going to be 0, and the driver of the motor is going to be off. Then we set DDRC. DDRC is the direction register port of port C, and that is going to be defined as input. So this defines this port C as an input. And then while 1, we repeat this loop until the condition holds. And then the statement is that if port C, the pin 0, this one, equals to 0, okay? So if this is 0, how can it be 0? When we close the switch, then we actually ground the voltage. The voltage right now is high at 5 volts through the resistor, but then when we close the switch, it will be grounded. So the voltage will be 0, and then this is going to start the motor. And then if we port B, which is this port over here, pin 0, and we OR it with 1, then we'll start the output if it is pressed. So this will only happen when this is going to be 1. So when we do OR of PB0, which was 0 before, and a 1 here, then we're going to start the motor. That's what we want to do when we push down this switch. And then else, if it's not pushed down, if port C, PC1, okay, if this switch over here is closed, so we're grounding this voltage and we setting this to 0, then if both PB0 and 0 together are 1, then we're going to set it. Otherwise, it's going to be 0, and then we will stop the motor. So that's a way where we can use the C in order to control a microcontroller and drive some kind of a peripheral device. Now, the peripheral equipment are various. It could be I/O devices like we saw before, the motor. There could also be memory. There could be various other devices like, for example, we can have displays, memories, and the microprocessor transmits the information in bits and bytes through 3 buses, the address bus, the data bus, and the control bus. They all go to all the devices. And then we have to make sure that the information between the device and the microprocessor or microcontroller are being synchronized. And that's basically what the adapters of the devices have to accomplish. We have here an example of various interface that between the I/O devices and the microcontroller. We see that we have here 3 ports, and 3 of them are connected to I/O devices like a temperature sensor, and that is the A to D converter as an example, as an interface. Over here to this port, we have a connection to a PC. And over here we have, through this port, we have a connection to a relay driver that actuates several drivers. So the task of the interface is to manage the CPU commands, to decide whether it's read or write, to synchronize the speed of communication, and make sure that the bits are compatible, whether they're in serial or parallel. And then it has to have features such as buffers, registers, latches to make connections, interrupt, polling. We'll take a look at this in a few slides. Handshaking, and then code conversion, such as we have from BDC to binary, and then A to D converters. Here's an example how the timing diagram goes for a microprocessor and peripheral equipment. This example shows over here pulses, which are at the clock is 5 megahertz or 10 megahertz for the processor, and the pulses are between 100 and 200 nanoseconds. And 4 of them is 1 bus cycle. And what we see here is that we have 20 bit address on a bus. We have 16 bits over here, A0 to A15. And we have another 4 bits address on this bus from 16 to 19. And then we also have on this bus 4 status bits on the same bus. And then we have over here ports that determine whether it's min-max mode. When it's high, it's min, which means that the CPU is in control. Then we have over here memory or I/O. When it's high, then we are doing over here memory access. And then we have over here the address latch enable. And when it is high, then we latch in the address. And that happens only in a first cycle, which means that this address over here combines with this address. So together, they become the address. And then from there on, the status over here is being conveyed on the second bus. Then we have over here read or write. Then we have a low is read and the high is write. So we're writing the address, and then we're reading the data from the device, the peripheral device, on with a low. And then we have over here the decision whether it's going to be on this pin, transmit or receive, and low is receive. So we are receiving the information from a memory, and this activates the data when it is low, this pin. Here's another example of so-called tri-state buffers. And what they do is they isolate the data. We have a data set coming in here on this port, another data set on this port, another data set on this port. They're all connected to the same bus. They have a common bus. However, we have a binary decoder over here, and depending on the code, if it's 00, for example, there are only 2 bits. So we have possibly 4 options. We need only 3. So if 00, for example, is given with A and B, A is 0 and B is 0, then we will enable A. So the signal will come out to A. All of these diodes will enable the signal, and the bus will be connected to data set A. Similarly, it will be done with the other data sets when they will be enabled. Now, there is a process called handshaking for the synchronization between the microprocessor and the peripheral equipment. And then the example here of the process that when the CPU reads information, then the peripheral sends data ready, a signal to the CPU. The CPU reads the data. The CPU sends input acknowledge to the peripheral, and then the peripheral can send another signal. When the CPU writes, the peripheral sends a peripheral ready to the CPU. The CPU sends the data to the peripheral, and then the peripheral can send another signal of ready to the CPU. There is a process called polling, where the processor is checking service requests from the peripheral. So the CPU runs the main program. The CPU continuously checks the peripheral request. The CPU jumps to a service subroutine when there is a request. It reads the I/O, updates the output, and then continues to the main. So this is done continuously being checked. A more effective way is to interrupt control, where the peripherals send the request when the interrupt request to the microprocessor. In this configuration, the CPU runs the main program. Then the peripheral sends whenever they need to send a request to the CPU. The CPU complete whatever it's doing on the instruction, and then it sends the interrupt to the service routine. It runs the service routine, and then when it's done, it updates the output and continues the main program. So this is a more efficient way to control it. So the CPU does not is not polling the peripheral. It's waiting for an interrupt request. This is an example of an interrupt programming of Intel 8051 microprocessor. For an example where there is a central heating system, and there are sensors, and the sensors actually generate an interrupt to the microcontroller, and the interrupts are as follow. We like to turn off the furnace if the temperature is greater than 21 degrees, and that is going to be in pin 3.2. And we like to turn on the temperature if the turn on the furnace if the temperature is less than 24.5 C. And that is by interrupt 1. So this is going to generate the output to the furnace, and that is on port 1, pin 7. So we have 2 ports, 2 pins on port 3, 1 pin on port 7, which are involved here. This is the general architecture of the 8051. And we see over here that the 2 interrupts, 0, 1, and 0 and 1 are coming into the interrupt control. We have here the CPU, we have the buses, we have over here the timers, we have the read-only memory, the random access memory, and we have various ports over here, serial ports for receive and transmit. There is also a time control register that also includes the configuration of the interrupts. And the configurations over here are defined that for either interrupt 0 or 1, then 1 defines the falling edge to trigger the interrupt, and 0 is a low level, is triggering the interrupt. And this is an example over here of the program that we do in assembly language to drive this heating system. And we start over here. We origin of the main program is at memory position 0, and then we jump to main. Over here, we define the position location of the interrupt service routine, which is service routine 0, and the position start at this hexadecimal location. And then in this case, we clear the pin 7 of port 1 when the interrupt 0 is turned on, and then this happens with the active low. The bar over here indicates that this will turn on when this signal is going to be low. If without the bar, it will be when this signal is high. And similarly for the interrupt of 1. So same thing here, the service routine 1 is starting at this location on a memory, and then we set P17 output to be high when we get the signal for P3. Now the main program defines the configuration of the interrupts. It starts at this location. It enables the interrupt 0 and 1, and that it sets the definition of IT0 and IT1, and then it sets the output over here to 1.7. It sets the bit. It set the bit, therefore output is on, so the furnace is on. If the temperature is less than 21 degrees, then it continues it as on, and it jumps from it jumps to here, which goes continuously until there is a change. If not, then it clears this port and it turns off the furnace. So this is an example of using the assembly program in running the peripheral example. This is the example over here of a display of a BCD. This is a binary code decimal that is given over here as an example. The number over here that we would like to put on the display is 0 to 9, and this is in decimal. However, the input that we come into a decoder, which is the interface device to the between the microprocessor and the peripheral display. This is a decoder interface. This receives a binary code, and if it is 0001, then we like to place a 1 here. If it's 1001, this is binary designation of 9. So what we have here in the decoder is we have the binary input coming in on 4 bits. And then we have 2 pins, RBI, which is the ripple blanking input. Blanking meaning just shutting off the display. And RBO is ripple blanking output. And the reason why we need this is because we like in this example to display 50, not 050. Like if we have 000 without the blanking, it'll be 050. So if we like to show 50, we need the blanking. So how does the blanking work? For blanking, the RBO has to be low. So when this is low, we get the blank. But to get this RBO low, we have to have both RBI and BDC low. So both of RBI and BDC must be low. So in this example, both of them are low. Therefore, we get a blank display. Over here, we get the RBO is 0. We can still feed it in to the RBI. And we have over here, the BDC is on, the RBI is off, and the RBO is on. So in order to get a display, both the RBO and the BDC have to be high. So we have over here the RBO high, and we have the RBI we have on. Okay, so this is the BDC is high, and and also so the RBO is high. So in this case, we also get a display here on the on this digit. We have an example over here of a multiplexing display with a BCD decoder, and we have over here that the BDC input. So this is 1, 2, 3, 6. We have over here 1, 2, 3, 5 bits, and then we have over here a illumination. Now the decoder provides the information to digital information to 4 of these displays, and then we have switching that decides which display is going to be turned on. So we could turn on this display or this one by turning on this transistor and regrounding the source. And then whatever was from the decoder placed on the display is going to be shown. And this is the multiplexing. Could turn out at high frequency such that the impression over here is going to switch between them very, very quickly, such that the number which was displayed by the decoder is going to show. This completes our presentation, and we'll talk more about PLCs in upcoming lectures.